Okay, so this is a talk, joint work with Ishai Mansour. It's kind of a nice work. We worked about it 2 years ago, and we kind of we neglected it, and it's kind of off track. And I think it has a lot of interesting open questions, and I think this is a very well-suited forum to discuss those. Okay, so the problem is that of discrimination. I'm going to describe it in a high level, nothing formal so far. So what is a discrimination? You have an algorithm, a function, or what we would call a discriminator. And the discriminator is provided with two data sets. Each come from some distribution, IID data. And what the discriminator needs to do, it needs to decide if the two distributions are distinct or whether it's the same distribution. And we would also probably want that if the discriminator says they are distinct, he should provide some sort of a certificate. Or in other words, he himself can be the certificate. So, so this task kind of won lately some attention. So discrimination, like I said, you have a discriminator, it gets to distribution, and what it needs to do is decide if the two distributions are distinct or if they are the same. And this kind of task won some focus lately. So I'll talk about it also in the context of learning. It's sort of a learning problem, but also you can think of it as a problem where, so lately people are interested in generating data that look like real data. So you have images, for example, of faces, and what you want to do is you want to generate, the computer wants to generate new faces. So there are these impressive algorithms lately called the GANs and VAEs and all sorts, that what they do is they generate fake faces. And within this task, one thing that you need to do is you need to decide when the two distributions are similar, okay? It's not sufficient, it's not the whole task, but it's a very important component in it. And one natural way to look at this problem, and this is how usually it is addressed, is to basically think of it as sort of a learning problem, or basically to think that this is learning. So, so what do I mean here by learning? So we're going to look at the classical PAC model, or some variant of it, where you have a learner that is defined by some class of hypothesis or context, as Amir said it, and you're given labeled sample from the from some distribution. So you have a distribution, and you get to see a domain and labels, and the learner needs to return some age which can predict the right label given data. So basically, you can reduce the problem of discrimination to the problem of learning, where you think of the two distributions as sorry, just where you think of the label data as basically synthetic and real. So you have a real distribution and a synthetic distribution, or distribution P1 and distribution P2. So you label data that comes from distribution P1 as 0, and you label data that comes from distribution P2 as 1. You give it to the learner, and the learner needs to learn a predictor. So if you can predict, if you can learn how to predict if something comes from P1 or P2, then this is a certificate that the two distributions are different, actually. Right? If it's the same distribution, then obviously you cannot distinguish between the two. So this motivates the following framework for discrimination, where you have a discriminator, which is defined by some class of distinguishers. So you have a class of functions or class of hypotheses, and then you define the notion that is called the IPM metric, or integral probability metric, which is dependent on your class age. So for each class age, you get a new metric. And the metric is basically you find the best hypothesis in your class that distinguishes between the two distributions. Okay, so the distance between the two distributions is the best distinguisher in your class. So given a class, you would want to construct a discriminator that if the IPM matrix between the two distributions is very large, epsilon large, then you want to return the discriminator or a discriminator that does well enough. And if not, then you may fail, okay? So it could still be that the two distributions are very distinct, but the hypothesis class doesn't distinguish, and then we allow the discriminator to fail. And it sounds like a compromise because you basically, at some cases, you fail. But on the other hand, if you look at the result in learning theory, it's not that of a big compromise, especially because usually in learning tasks, we don't actually care about discrimination in some statistical sense. We usually would care that, you want the two distributions to look alike in the sense that no computationally efficient machine can distinguish between the two, right? I mean, I don't care if there is some statistical difference between fake and real, if the fake can fool any machine or any attempt to distinguish between the two, or to, like in security, definitely, that's all I want, right? I want to fool someone, and that's all. So this is one way to look at learning, to look at discrimination. And then you can have this trade-off between expressiveness and sample complexity as usual. So you have a domain, say N, and you want to find some discriminator defined by some hypothesis class. And you can basically have a trade-off between simplicity and expressiveness. So you would have, for example, you could take over N the class of singletons. So your discriminators are defined by points, and every time you see that point, the discriminator says 1. So the hypothesis says 1, and you can prove cluster result in learning. This class has VC dimension 1, so you would have nice sample complexity. You can observe 1 over epsilon square points, and then you can train your discriminator to pass this IPM test. Obviously, the trade-off is that it has small distinguishability, meaning you're measuring the IPM distance, but the IPM distance is very, very far from the statistical distance. So a lot of distributions that look alike, but in terms of, that are far away, but if you look at the IPM distance with respect to singletons, then they are very close. On the other hand, you can take as your hypothesis class, you can take the whole set of functions. In that case, you would need to see a lot of examples. So if you want to pass this test, if you want to learn this test and do discrimination, then you would need N over epsilon square examples, which can be very, very bad in many cases. On the other hand, the distinguishability is very nice because you are basically learning the total variation between the two distributions. Okay, so this is how you would look at this problem from a learning point of view. Sorry, why is it not passing? Okay. Oh, so I need to clear. Yeah, so another way to look at this problem is from the property testing point of view, where, so this is very similar to basically learning the L1, or total variation. where you are given two distributions over n elements and you wish to check whether these two distributions are statistically close. So here you are measuring the total variation. And the nice thing is that the discriminator is very, if you have enough data to make this, to do property testing, this is very nice because you can actually decide if the two distributions are close or not in a very strong type of metric, much stronger than IPM. However, to do that, to actually perform property testing, you would need order of your domain number of examples, okay? So maybe not n, but n to the 2/3 or square root n, which is far from practical. So for example, if you wanna discriminate between two distribution over images, then it's exponential in the number of bits, in the number of pixels, sorry, and that really is not very practical. So now I want to talk about some setups that will be similar to the learning perspective in the sense that it is scalable in terms of sample complexity, where the trade-off is obviously, okay, we're not going to learn the total variation, we're going to learn something much weaker, but on the other hand, it's going to scale nice. And first, I want to give you an example to why you might want to think that learning is not the whole story. So maybe there are things that we can do that are not like learning. So here is a proof of concept example. Ah, shit. Why is it? Ah. Okay. So here's a way, here's, for example, a discriminator, which a priori is not defined by some hypothesis class, or it does not do a learning task. So here's how I want to discriminate between the two distributions. So remember, I'm looking at something like IPM distance. I don't care if I will always succeed in distinguishing, but I do want to sometimes be able to distinguish. And what we can do is, for example, a collision test. So what happens in a collision test? In a collision test, we're going to draw two examples at each round from every distribution. And we're going to check what is the probability that the two samples are the same. Okay, so I have distribution P1. I'm taking two examples from it, and I'm observing if I saw the same example. And then I take 2 points from P2, and I'm observing what is the probability that I drew the same point twice this time. So obviously, if the probability of this event is different in P1 and P2, then P1 and P2 are different. Okay. If not, again, doesn't say anything, but I can say this is my test. Okay. And this test is not, at least a priori, it's not defined by some hypothesis class. If you would think about it a little bit, it's not that far from just checking what is, like doing a singleton test, checking what is the probability of some event, of certain singletons. Because if there are no fat singletons that have high probability, you would also not have collision, and vice versa. But at least formally, this test is not defined by some hypothesis class. So we can think of a general framework which goes beyond learning or beyond testing with a hypothesis class. So what we're going to do is we're going to take some graph over our domain. So we're going to think of, so you can think of it as a Boolean function over pairs from your domain, or you can think of it as a graph. And the type of tests that we're going to do to check if the two distributions are the same is we're going to draw IID, two examples from P1. And we're going to see what is the probability of an edge, or what is the probability that the pair x1, x2, the function g gives it value 1. We're going to check what is the probability to see an edge when we draw two vertices from P2. And again, if the two are distinct, then obviously it's not the same distribution. So we can declare that the two distributions are distinct, and if not, it fails. Okay, is that clear, the idea here? That what is the graph here? How is it defined over the domain? Or I'm assuming that yes. And now we can take it more generally. And
to clarify, wait.
Yes.
To clarify, then you basically define, so before you define the distance over distributions by taking a family of events, the class, and taking the supremum of the...
Yeah, so far I'm not taking any supremum. I'm just saying a single test, not... Right?
Just one test, okay.
Yeah, I have one, like one hypothesis, one test.
Yeah, so...
Okay? But obviously the natural thing is to take a family, right?
Right, okay. So now the family is just not of events of X, but events of X squared, and then you take pairs and you check whether they belong to this event.
Exactly. So now I have a family of graphs over my domain, and the IPM distance defined by this family of graphs is going to be where I choose the graph that most distinguishes between P1 and P2. Well, what does it mean distinguishes? The probability to draw an edge, if you draw 2 points IID from P1, is different from the probability to draw an edge if you draw 2 points according to P2. Okay, so in this case, the two distributions will be considered different. Okay, so this is now a generalization of the IPM metric. If before I took hypothesis class, now I'm looking at the graphs. Okay? And was there something I want to say? Yeah, okay, so I'll just, so I wanted to give a concrete example. So let's think that our domain is a Euclidean space. So you could take as a single graph, for example, some metric neighborhood. So let's say that 2 points are related or have an edge if the Euclidean distance between them is smaller than half. Okay, 1, whatever you want. And if they are far away, then there is no edge between them. So in this case, what we're measuring is what is the probability that we will draw 2 points that are at distance 1 or half from each other. And then you can take a family in the sense that you can take several types of metrics. Okay, maybe you believe that there is some metric that distinguishes between the two distributions in the sense that one has small radius, the other doesn't have small radius, but you don't know what is the exact metric, so you take a family of metrics, like metric, all Manabolic distance, something like that. Okay, so this could be a concrete example for a discrimination using some family of graphs. Okay? And now you can obviously think of an even more abstract, this is a typo, say what you do here. So you can think of hypergraphs, right? So you have a family of hypergraphs with a k, each hyper edge in a subset of size k. And then, okay, so it's not P1 over 2, it's you draw k points IID from P1, and you check what is the probability of an hyper edge, and you draw k points from P2, and again, you check what is the probability of an hyper edge, and if it's distinct, then the two distributions are distinct. Okay? So, okay, so now what we did is we defined this new framework for discrimination or for constructing discriminators. And we will call these distinguishers graph-based distinguishers because they are based on graphs. And now you have two very, very natural questions, okay? First is, how strong is it? So is it really that different? Because like I said, here is a graph-based distinguisher collision test. Okay, it's formally it's different, but like I said, it's not that different from the class of singletons, right? So I do have some hypothesis class which provides me exactly the same test and succeeds on exactly the same cases. So the first question is, can I even construct some graph-based distinguishers that are successful whenever, even though a classical distinguisher, some hypothesis class, would fail. And in this respect, I have to say, for me, the intuition was that no, you cannot do something better with graphs, because if you remember, or maybe I'm telling you this, but it's kind of known that the VC dimension says that learning is about choosing an hypothesis class. Basically, at least in the PAC setting, if you want uniform conversion, if you want uniform learning with uniform sample complexity, then there is nothing you can do better than choosing some hypothesis class. And discrimination and learning are not that different, if you think about it. Basically, to predict if something comes from P1 or comes from P2 is not that different from basically declaring that the two are distinguishable. So you cannot do learning that is not related to some hypothesis class. And the second question, okay, so let's say we tackle this and we can show, we're going to show it in a minute, that you can do something with graphs that you cannot do with hypothesis. And then we're going back to the game of VC dimension. So we want to define the sample complexity. How hard is it to distinguish? How many examples do I need, and so on. Okay, so that's our roadmap for the rest of the talk. I want to talk about these two questions. What can we say about the expressive power of graph-based distinguishers? And second, what can we say about their sample complexity? Okay, so I'm continuing. Now, okay, so in terms of the expressive power, what we can show, so the first theorem is that if you take an infinite domain, then you can construct a graph, a single graph, such that for every hypothesis class, H, that has finite VC dimension, which is necessary if you want to learn with it, then there are going to be two distributions that the hypothesis class cannot distinguish between them. Okay, so they're indistinguishable. So the hypothesis class fails to identify synthetic from real, but you can, the graph that you generated will distinguish between them. Okay, so I will emphasize the quantifiers here. The graph is universal. It is not defined by the hypothesis class. The no-3-lunch theorem said that for every hypothesis class that is learnable, you can find another hypothesis class that can succeed while that one failed. Okay, this is a no-3-lunch that says no hypothesis class can be optimal, but this theorem says something else. It says that you have a single graph that is, it's not better, but it is incomparable to any hypothesis class. Okay, there is no hypothesis class that succeeds whenever this graph succeeds. Okay, so that means that graph-based distinguishers are more powerful, are different. They are different tests than any hypothesis class. They will induce an IPM metric that cannot be defined by some hypothesis class.
But wait, you also mean to say probably that this graph hypothesis class, or however you call it, is can be estimated from samples.
Okay, so it's a single graph. It's not even a family. So it's a standard Chernoff bound that it can be estimated. Right? That's why it's important that it's not a family of graphs that are defining the IPM distance, but a single graph. So once it's a single graph, it's a standard Chernoff bound that, yeah, you can estimate the IPM distance estimated by this graph.
There is a single event defined on pairs that the IPM distance with respect to this particular event is a particular single.
Yeah, it's not even an IPM distance. It's a very, very naive or IPM distance. It's a single graph.
Single test, okay.
Okay, so here's the proof. It's kind of it's not that complicated. So let's do it. So the idea is follow what we're going to do is we're going to consider a graph with vertices that I'm going to index by a natural number, and it's a bipartite graph, and the one side is going to be indexed by natural numbers, and the other is going to be indexed by all subsets of natural numbers. You can take only finite. Okay, it's not about something about the power. Okay, this can be, in this example, I'm going to take all subsets. I'm going to use just finite subsets. Okay, so everything is finite. The graph is infinite, but each subset is a finite subset. And what we're going to do is we're going to draw an edge between a subset and a point if the point belongs to the subset. Okay, so this is the graph. And what I claim is that this graph is incomparable for any hypothesis class. So how am I going to show that? So let's say you have an hypothesis class. And what I want to do is I want to generate a distribution that is indistinguishable between the two with respect to age, but the graph succeeds. So here's how I'm going to construct it. What I'm going to do is I'm going to draw two samples, S1 and S2, from one distribution that is going to be on a very, very large support. I'm going to say about how large in a minute, and why do I need it to be large, but uniformly. And I'm going to draw each sample by drawing VC over epsilon squared number of examples. Okay, so I'm going to take some distribution, uniform, supported on a very, very large domain, finite, and I'm just going to draw twice two samples of side VC over epsilon squared. So what's going to happen? So two things are going to happen with high probability. In particular, we're going to find some S1 and S2 that will satisfy what I want. First, the two samples are going to be distinct. The intersection is going to be empty. Why is that? Because I just drew two samples from a very, very large support. Okay? Now, the second thing that is going to happen, which is important, is that the IPM distance between the empirical distribution over S1 and the IPM distance and the empirical distribution on S2, they are going to be very close. In other words, the hypothesis is not going to be able to distinguish between S1 and S2. And why is that? Well, that is basically the result of the VC theorem that said, the epsilon approximation result that said that if you draw VC over epsilon squared number of examples, then you get a distribution that is indistinguishable from the original distribution. So if I draw two examples from that distribution, both of them approximate the original distribution. Therefore, they are both indistinguishable because they both look like the real distribution. And that's why basically you can do learning. You can draw enough examples so you can make all your tests on a finite empirical data set, which looks like the real distribution. So okay, so what I did so far is I drew these two two samples, and now I'm going to have a distribution where I'm going to take S1, and with probability half, I'm going to draw the subset that represent S1, and with probability 1, I'm going to draw a point from S1. Okay, to draw a point from PS1. That's one distribution. The other distribution, again, I'm going to draw a point from the subset S1, the vertex that is indexed by S1. And with this probability half, I'm going to draw a point from S2. So now you can see that the probability to draw an edge with respect to P1 it's half. Okay, you just, sorry, 1/4, right? No, half. No, 1/4, right? I need to draw, yeah, 1/4. You know, okay, it's a constant, and you know it better than me. But okay, the second one I know that's easy. It's going to be 0. Okay, you cannot draw an edge if the subset S1 is not connected to point in S2 because the two don't intersect. Okay, so the graph distinguishes between the two. On the other hand, the distribution, the hypothesis class, is unable to distinguish. Okay, so what we showed is that the graph-based test is incomparable to any hypothesis class. It does something else, which is in my I don't know, I get confused by this quite a lot every time because it looks like you're doing learning with something that is not an hypothesis class. And in some sense, yeah, this result says that if you look at all these distributions, then if I use this relation, I am doing some prediction which I couldn't do with any hypothesis class, right? So you have this learner that finds a single point which hints to what is the correct way to label the others, and magically you are predicting something that shatters the whole domain. Okay.
What confuses me a little bit is that you only consider the hypothesis classes over the right side of this graph.
Yeah, I'm not considering. No, I only care how the hypothesis class looks like on the right hand side.
Yeah, but you could ask like about what if you have an hypothesis class of a finite VC over the entire domain, which also includes.
No, the hypothesis class is defined over the entire domain. But what I claim is that with these two distributions, P1 and P2, the hypothesis cannot distinguish because you don't really care what it says on the left side, because the only point that comes from the left side is the set S1. So it's the same in the two distributions. The probability to see S1 is the same on each distribution.
Okay.
And it looks different and it also looks the same on the right hand side. Okay. So yeah, the hypothesis class is defined on both sides, but I just don't care what happens on the left. Okay. Because the left side it actually looks the same in the two distributions. The two distributions on the left side are the same.
Thanks.
So what if your test contains only the right side is a member of H? Won't this also distinguish P1 and P2 with probability 1/2?
Can you repeat it slowly?
Yeah. So suppose H contains the set of all the vertices on the right hand side.
So there is an hypothesis in H that is one on all the hypotheses in the right hand side, or is it just that distribution?
Right.
Okay.
Yeah.
So your hypothesis class is a single hypothesis, and it is one on the right side.
Yeah.
Okay.
Wouldn't that distinguish P1 and P2 also? Probability 1/2?
Why? S1 has probability. So if you draw samples from P1, you see one with probability 1/2. And if you draw from P2, you see one with probability 1/2 also.
Okay.
Right? Or maybe I didn't understand the example.
Right.
Okay, so we have a finite version of this test. So yeah, I took an infinite graph. You might want to ask, what happens if my graph is finite? Can I still do something, some sort of indistinguishability between the two? So now, basically, okay. So first of all, because the graph is finite, you can learn the total variation in time with sample complexity with sample complexity n. So you cannot expect that you have some graph that does something that cannot be done by any hypothesis class. But you can still get some upper bounds and lower bounds, and you can show that the VC of the class H would need to scale logarithmically with the size of the domain if the hypothesis class wants to compete with our graph. And you can imagine it, we just take this construction and we see how many vertices we actually needed in order to construct it. And you get that you need 2 to the n number of examples. And we can also, so in the original paper with Ishai, we did not get the upper bound, but we can also show that there is an upper bound. So for every graph with VC dimension that is large enough, log n, you can do anything that the graph can do. Okay, so so these are the rates. Okay. So this, so now we go to the second question of sample complexity. So given a family of graphs, how many samples do I need if I want to do the distinction? So remember, for an hypothesis class, you can do the discrimination if you have VC over epsilon squared. So, and you can also define the VC over graphs, over a family of graphs, when you think about it as a function from 2 array to 0, 1, and that would define a VC dimension. So you might want to think that this is the right measure, but it turns out that no, you could have infinite VC dimension family of graphs that are, the sample complexity is finite. So for example, if you take one regular graph, then the probability to estimate the probability of edge with respect to all one array graph is not that different than just estimating the probability of the vertex, which is the singleton hypothesis class. So the sample complexity is finite, even though as a family of hypotheses over vertex over edges, it has infinite VC dimension. It turns out that the right notion is what we call here the graph VC dimension, which is defined as follows. So you look at all the hypothesis classes that you get by fixing one x. So you take an x, and now the hypotheses are all the neighborhood class. And this class has a VC dimension. And the graph VC dimension is a supermoon over all the possible VC dimensions. Okay. So it's kind of intuitive that this would be sufficient. If this size is small, then you can learn. You can do discrimination, and it turns out that it's also necessary. But we are leaving some gap. We know that graph VC dimension is sufficient. Our lower bound is not graph VC dimension, it's square root. Okay, so there is some gap here. In VC dimension, it's the same, right? It's a tight bound. Here there is some gap. I don't think I have time to go over the proof. So I'll skip it. Let me just mention some questions. So like I said, the first open question that we have here is square root here the right bound? Yeah. The second another set of open problems that we have is what happens if we go to hyperedges. So I didn't talk about hyperedges, but you can pretty much imagine how this theory extends. Everything I said extends to hypergraphs. The graph VC dimension is defined by fixing all points other than one point. And here there is a very loud dichotomy in the sense that so don't even look at the square root. This is probably can be fixable, that the question I asked before. But in terms of the dependence on the size of the subset, the upper bound is k squared, and our lower bound is exponential, so inverse exponential in something polynomial. Okay, k to the cube, I don't remember. I'm not even sure that the polynomial we provide in the proof is tight, but I think what is definitely more interesting to bound is how the number of edges, the number of subsets in the hyperedge change this. So for some reason, the proofs that we make is very sensitive to the number of hyper edges, because you do this test and you need to see some event of how the sets are, what's the probability that you will see some sets. And I think this can be improved. Definitely worth improving. Another open question, yeah. So the proof I gave you provides a bound of square root log n when you draw two samples. You can actually do better. It's not that hard. In the case of graph, you can show epsilon square log n. The proofs we provide for the hypergraph case of the sample, of the expressiveness are still with square root log n. And again, I think this can be improved to log. I think this is it.
Okay, thanks, Roi. Thank you very much. Maybe we have time for one quick question, if anyone has. We also asked some questions during the talk, so
I have one question. In your definition of IPM, could picking X1 from P1 and X2 from P2 give more information, like mixing the samples?
Yeah. So that's also a good point. You can also think of other tests that are not what we call graph-based. For example, what if you take from P1, P2, and then P2 to P1, that would be the same. Or if you have a directed graph, you could ask what happens if I first draw from P1 and then draw from P2 and first from P2. And yeah, this is a very nice question. Yeah. Of how universal this approach of graphs. Yeah.
Yeah, maybe the most general mode is that you have an ordered access to both of them, and you can apply any algorithm that involves whatever the finite sample complexity from both.
Yeah, that would be the definition.
Yeah.